plus 12. In today's video, we are going to discuss the topic diffraction of light. Okay, we've already dealt with interference of light. Now we are going to discuss diffraction of light. Now, what is this diffraction of light? Diffraction of light is a phenomenon of bending of light. Now we've studied about, in the junior classes, we've studied about rectilinear propagation of light, that light travels in a straight line. Okay, but here we are going to see that we are going to study that light also undergoes bending. Light does not always travel in a rectilinear path. We've also studied about refraction of light. In refraction of light, light bends. Light, the phenomenon of bending of light. But when light travels from one medium to another, it has to travel from one transparent medium to another transparent medium. Then the phenomenon of bending of light is what is called refraction. But here, diffraction, it's in the same medium, remember. Okay, so the phenomenon of bending of light, when it travels through a small slit or phenomenon of bending of light around the corner of some obstacles, okay, provided the size of the obstacle or the width of the slit or the aperture is comparable to the wavelength of light. Okay, and then bending of light happens, which is called diffraction of light. If the size of the slit or the obstacle is not comparable to the wavelength of light, it is much bigger than the wavelength of light, then bending of light does not happen. Then diffraction does not happen. Like, a window is also a slit, so to say, but it is a slit which is much bigger compared to the size of, compared to the wavelength of light. Therefore, the light simply passes through the window. Okay, so, and no bending of light happens. So in that case, rectilinear propagation of light is true. So diffraction, which is bending of light, is true only under a certain condition, that is the size of the slit or that of the obstacle. Round the corner of the obstacle also diffraction takes place, bending of light happens. Okay, but the size of the obstacle or the size of the slit has to be comparable to the wavelength of light. So in that kind of a scenario, we will see bending of light happens, which is called your diffraction. Now, diffraction can be of two kinds. One is called Fresnel, Fresnel. This is the name of a person. It's not read as Fresnel. Okay, it is Fresnel diffraction. This also is the name of a person, Fraunhofer diffraction. In Fresnel diffraction, we have a source of light. Okay, and we have a screen, like in case of interference. The distance between the source of light and the screen is finite. Whereas in case of Fraunhofer diffraction, the distance between the source of light, okay, you have a slit also. You can also see the distance between the source of light and the slit is infinite. Also, the distance between the slit and the screen is also infinite in case of Fraunhofer diffraction. Whereas these distances are finite in case of Fresnel diffraction. Now, in your syllabus, we only have this topic, which is Fraunhofer diffraction. So we are going to discuss about Fraunhofer diffraction only. Just wanted to give you an information regarding this, that this kind of a diffraction also happens. Now, if these distances are to be infinite in case of Fraunhofer diffraction, how do we get Fraunhofer diffraction in the lab? Now, what happens is these distances are to be infinite in case of Fraunhofer diffraction. Now, if the source of light is infinite, then what kind of ray of light do we get? The kind of rays that we get is parallel rays of light. We can consider the sun to be, infinite distance away from us. So, the rays of light that we get from the sun, we can consider the rays of light to be parallel beam like this. Alright, so if the source of light is infinite, we should be getting parallel beam of light like this. Now, in order to get parallel beam of light, if somehow we can get parallel beam of light in the lab, then we can consider the source of light to be at infinity. Now, how do we get parallel beam of light in the lab? What we do is we use a convex lens, okay, such that this source of light here is giving rays of light this way. Okay. Uh, so what happens is a diverging beam of light, so to say. So this ray of light is made parallel by your convex lens. So it makes parallel. So it's like the source of light and the slit is infinite distance away. Okay. So this is how it's done. All right. So this is form of a diffraction which we are going to discuss about now, and I hope this the phenomenon of bending of light. I believe you've understood the definition. Remember, this is a very important condition. The size or the width of the slit or the obstacle has to be comparable to the wavelength of light. Only then bending of light happens. Now we are going to look into Fraunhofer diffraction. Okay, but first let me tell you, when we discussed interference of light, okay, then also, diffraction, interference of light, the Young's double slit experiment is not possible without diffraction of light. Then also we actually dealt with diffraction of light, and mind you, diffraction also is a phenomenon like interference which is exhibited by waves. Okay, so what happened was, in case of interference of light also, if this was one of the slits, so what happens is you have rays of light coming this way, parallel rays of light coming this way. Okay, now this slit, according to Huygens principle, every particle lying on this will be vibrating in phase, and this slit also therefore acts as a new source of light. Now, this new source of light or wave gives out waves this way. If this is water waves, if this is a source of disturbance on the surface of water, then ripples are generated this way. These ripples are going to hit this slit. There's a slit and a small opening over here. Alright. Now this opening will also give its own wave. This opening also will act like a new source of wave and will start giving waves in all directions like this. So to say, the waves are going in all directions like this. Okay, it's going out like this in all directions. Alright, now if it is a source of light, what we expect if this is a source of light and we have a small opening in front of this source of light, what we expect if parallel rays of light are coming, say for example, if parallel rays of light are coming and hitting the slit, we expect, and we have a screen, we expect only this portion of the screen, which is right in front of the slit, only this portion of the screen to get brighter, to become bright. And of course, that is true. That is true if the slit is large compared to the wavelength of light. If this is a window of your house, then what happens is, obviously only this portion will be brighter, and this tells us about the rectilinear propagation of light. But if the slit is comparable to the wavelength of light used, then what happens is this slit will also act like a new source. Okay, new source of wave. Alright, thereby giving out light in all directions like this. Exactly like in case of water waves. Okay, this was exactly as in case of water. Diffraction of light also, the phenomenon of bending, so to say, becomes true. So light initially was coming in a straight line, parallel rays of light, okay, but then after passing through the slit, which is of the size comparable to the wavelength of light used, what happens is the ray of light starts bending. This phenomenon is what is your diffraction of light, and we saw this happening in case of interference of light. So in Young's double slit experiment also, this was our source, okay, and we had our two slits. So ray of light was coming this way, ray of light was coming this way, okay. Then what happened is, through these slits, diffraction happened. Diffraction took place through these slits. These slits, I told you that then also, in the video also, the slits are very small, comparable to the wavelength of light. And what happens is, These two slits, they act as two different sources of waves and thereby they interfere. Therefore, on the screen, at different points, we get bright and dark fringes, alternate bright and dark fringes. The shaded one representing the dark fringe and the unshaded boxes here representing the bright fringe. So, rays of light bends through this slit, goes in this direction also, rays of light bends through the upper slit also, goes in this direction also, and they interfere. Different ways they interfere. So diffraction is taking place then also, in this case also, so to say, remember that. This phenomenon of bending of light is what is your diffraction. Now, let us talk about Fraunhofer diffraction. So, let me erase these things. I hope the picture is clear. Okay, if it isn't, you can recap, you can rewind the video. Now, in case of Fraunhofer diffraction, we have the screen, we have the source of light, the single source of light, okay, which is giving us light, we have the lens, and we have a slit. This is a highly magnified picture of the slit, remember. The slit width should be comparable to the wavelength of light that we're using, and let us suppose that the slit width is small a. Small a is the width of the slit. Now, the rays of light after passing through, after coming out rather of the lens, what happens is they come out, they become parallel and they come and hit the slit. Now the portion on the screen just in front of the slit, you obviously get a brighter side over here, brighter fringe, so to say. Okay, so this is the maximum that we get in, right in front of the slit. And this is the intensity graph that I've drawn over here. Intensity in case of diffraction, Fraunhofer diffraction to be more precise. And you see that unlike the case of interference, where all the bright fringes were equally lit, it was like this. It was like this in case of interference of light. But in case of diffraction, you can see the bright fringes, the maxima, are not equally bright, are not equally lit. It is the central maximum which is the brightest, and then after the other maxima, you can see the intensity goes on decreasing. The brightness goes on decreasing. Yes, they are maxima, but the intensity is lesser compared to the central maximum. So this is the diffraction pattern this is the diffraction pattern and this is the interference pattern. Alright. Now what we are going to discuss is so we've understood how we get the central maximum because rays of light coming from here, they come and hit the central portion on the screen, and what happens is, since they travel equal distances, so the path difference between these two rays of light is zero, and we know for constructive interference, if the path difference is zero, then what we get is we get constructive interference. The conditions for constructive and destructive interference still applies, remember, anyway, because the rays of light are anyway interfering with each other. So since the path difference is zero, another ray will start from a point just below, another ray of light will start from point just above. They also interfere constructively because the path difference is zero at this particular point, and you get a bright fringe. So this is how we get a bright fringe. Now let us understand how we get the first dark fringe. So this is the first dark fringe on the upper side, first dark fringe on the lower side. This is the second dark fringe, remember, upper side. This is second dark fringe on the lower side. There is a central maximum, first maxima, this is also, second maxima, second maximum. Okay, so we are going to now discuss how we get the first diffraction. Sorry, first dark fringe. In order to understand how we get the first dark fringe, what we do is we consider this single slit to be made up of two halves. Okay, as if these are two different slits, although it's not, remember, such that the width of each half is now a by 2. The whole slit has width a. So this half has a by 2. The lower half obviously will have, width a by 2. Now what happens is, so since these are like we are considering these to be like two different sources now. So a ray of light starting from the upper slit, the uppermost part of the upper slit traveling in this distance. Then a ray of light from the uppermost part of the lower slit travels this way. Okay, parallel they are going. And let us say they are moving at an angle theta with respect to the horizontal. Now, of course, do not forget, we have, since this is frontal diffraction, we have a lens somewhere over here. Now, this lens is what is, since these are parallel rays moving in this direction, this lens will converge the rays of light at this particular point, remember. So this is how Fraunhofer diffraction takes place. So what we now do is, since these are two parallel rays of light starting from two different sources, so what is the path difference between these two rays of light? Now, in order to understand that, what we do is we drop a perpendicular from this uppermost point. We drop a perpendicular on the lower ray of light. Okay, so this length is a by 2, mind you, and this is the perpendicular that we have dropped on the lower ray of light. This is the horizontal, and the angle that these rays of light makes with the horizontal is theta. Now, if that angle is theta, then this angle also is theta. Let me name them. So A, B, C. The point where we've dropped the perpendicular is C. So let me, magnify this triangle over here. So it's like this. So we are saying this is A, this is B, and this is C. So this angle is theta. The length AB is A by 2, small a by 2. Now what we want to do is, we want to know this distance, AC. Whatever is this distance here, this distance AC is the path difference between these two parallel rays of light. Why? Because this is the extra distance which this lower ray of light is traveling. AC is the perpendicular which we've dropped, remember that. So, sorry, BC is the perpendicular that we've dropped on the lower ray. Okay, so AC is the extra distance which the lower ray has traveled. They are parallel rays of light, mind you. Now we want to find AC. So what is AC? We know this, okay, this length. So AC, we know sine theta is perpendicular by hypotenuse. Okay, since this is the perpendicular here, so this has to be the hypotenuse. So AC, that is what we want to find. BA, not BC. This BA. BA is the hypotenuse. So BA is A by 2 sine theta. So AC is A by 2 sine theta. So the path difference between these two rays of light is, let me write over here, A by 2 sine theta. Now we know from the condition for dark fringe that if the path difference is an odd number multiple of lambda by 2, we get, a dark fringe. Now, if the path difference between these two rays of light is lambda by 2, therefore it should be a dark fringe. And this happens to be the condition for the first dark fringe, which eventually comes out to be A sine theta is equal to lambda. So this is the condition for your first dark fringe, remember that. Okay, likewise now let us see how we get the first maximum. The story for the first dark fringe on the lower side is also the same, remember that. Okay, now we want to see how we get rather the first maximum. For the first maximum, let me erase this picture now. So in order to get the first dark fringe, what we did is we divided the slit into two equal halves having length a by 2. Now in order to get the first maximum, what we do is we divide the slit into three equal halves, such that it's like three different slits now operating, and the width of each of the slit is now a by 3. So the story is very similar. The rays of light are moving from the uppermost part of the first slit and the uppermost part of the second slit. They're moving in this direction. Alright? And of course, we have our lens, which is going to converge these rays of light at this particular point. And by the way, the angle which they make with the horizontal is a bigger angle now, bigger than this theta. Okay, because the first dark fringe is on the lower side, lower than the first maximum, so the angle at which the rays of light are moving should be smaller. So, but still, let me call it theta. All right. Now, what will be the path difference? The path difference between these two rays of light will be a by 3 sine theta. If this is theta, this angle is also theta. You can check that yourself, verify that yourself. So, again, if the path difference is lambda by 2. But mind you, if the path difference is lambda by 2, we are going to get a dark fringe. And we are talking about the maximum bright fringe. So why are we using the condition for a dark fringe? We are using the condition for dark fringe because a ray of light moving in this direction, okay, it interferes destructively with the ray of light starting from the second fringe. And not just that, I forgot to tell you in the previous case also, every ray of light, a ray of light starting from just below a source on the first slit, it interferes destructively with this ray of light, this source, ray of light starting from this source on the second slit. In fact, what happens is every ray of light starting from the uppermost slit has a corresponding ray of light on the second slit with which it interferes destructively. Okay, so to say, the whole beam of light starting from the first slit, it interferes destructively with the whole beam of light starting from the second slit. So to say, they cancel each other out. But we still have the third slit. This third, the rays of light starting from the third slit, it has nothing to interfere destructively with. And thereby, the rays of light starting from the third slit, they simply reach this point, thereby giving us a maximum. Okay, so since only 1/3 of the rays of light are reaching this point, thereby we get a maximum having a decreased intensity. This accounts for the decrease in intensity when compared to the central maximum. In case of central maximum, all rays of light coming from the slit were directly reaching this point, and thereby we got the brightest maximum. Whereas in case of the first maximum, only rays of light starting from 1/3 portion of the slit reaches. Alright, in case, so this is your condition for the first maximum, or I can write this as a sine theta is equal to 3 into lambda by 2. This is for your first maximum. This for your first maximum. This for your first minimum. Okay. In case of the first dark fringe also, I forgot to show, remember, since the slit was divided into two equal halves, a ray of light starting from the uppermost part on the uppermost slit interferes destructively with the ray of light starting from the lower slit. And every ray of light starting from the upper slit has a corresponding ray of light on the lower slit with which it interferes destructively. So the whole band starting from the upper slit interferes destructively with the whole band of light starting from the second slit. And thereby we get the first dark fringe stream. Okay. Now, in order to understand the second dark fringe. How do we get the second dark fringe? In order to understand the second dark fringe, we divide the slit into four different parts, four different halves, so to say, each of with a by 4. So this is the slit. So this is the slit. We divide it into four equal halves. 1, 2, 3, 4. Okay, each of with a by 4. Now the whole band of light starting from the first slit interferes with the whole band of light starting from the second slit. They cancel each other out. Likewise, the whole band of light starting from the third slit interferes destructively with the whole band of light starting from the fourth slit. Thereby, they also cancel each other out, giving us the second dark fringe. Okay, now what will be the condition for the second dark fringe? The path difference will be a by 4, a by 4 sine theta. All of these thetas are different, remember. This is the smallest theta, then this is a bit bigger. This will be the bigger than these two, a value bigger than these two. So the path difference is lambda by 2. Then we get the dark fringe, the second dark fringe, and thereby we get the condition is a sine theta is 2 lambda. This is for the second dark fringe or second minimum, second dark fringe. In order to understand the first maximum, we divide the slit into 5 equal halves now. We have one more slit over here. One more slit, each of width a by 5. That is how we understand. Okay, so the first beam of light starting from the first slit interferes destructively with the beam of light starting from second. Beam of light starting from the third fringe interferes destructively. Third slit interferes destructively with the beam of light starting from the fourth slit, and the beam of light coming from the fifth slit has nothing to interfere with, and thereby this beam, it reaches this point. Only thing is, since this is 1/5 the intensity of the central maximum, thereby the intensity will be lesser than the central maximum, and it will be lesser than the first maximum also. Because in case of first maximum, 1/3 the intensity was reaching. In case of fifth maximum, only 1/5 the intensity will reach. Okay, likewise, you can calculate for the third dark fringe, the third maximum also. Alright, but that is absolutely not needed. What you only need to understand is, or you need to remember is this equation. That is the condition for the first dark fringe. Because based on this, you will get numericals. Now, if you ask me, what is the general condition, so to say, for the dark fringes? So the general condition for dark fringes, you can see a sine theta is 2 lambda, a sine theta is lambda. We can write, these are for dark fringes, we can write a sine theta is n lambda. This is the general condition for DF dark fringes. And likewise, if you ask me, what is the general condition for bright fringes? So this is for the bright fringe. Where is that for the a by 3? Yeah, this is for the first bright fringe. For the second bright fringe, it will be a sine theta is equal to 5 lambda by 2. Alright? Now, therefore, what we can write is a sine theta is equal to 2 n plus 1 into lambda by 2. This is the condition for the first, this is the condition, so it is a general condition for the bright fringes in case of diffraction. This is for the bright fringe, this is for the dark fringe. Now, like I said, based on this equation, you are going to get numericals. Alright, very, very easy numericals. Okay. Now, one thing I want to tell you, sometimes you get to calculate, let me erase these things. What you will get to calculate is, you will get to calculate the angular width of the central maximum. That is, you will get to calculate, measure this angle, the angular width of the central maximum. Now, how do we find that? Okay, it should be like this actually. It should be measured from this point, from the slit itself. So you will be asked to calculate this width. Okay. Now how we do that is the distance between the two first dark fringes also is the distance of the central maximum. So if this angle is theta, theta in case of the first dark fringe, then this is theta that we are talking about for the first dark fringe. Okay, so the width of the central maximum, so to say, is theta plus theta, so 2 theta. So in order to calculate the central maximum, also you need to use this thing only. You'll be given the value of lambda, you'll be given the value of a, so you can calculate sine theta, and thereby you can calculate the value of theta using your calculators, of course. So if you can find theta, then 2 into theta will be the angular width of the central maximum. This is how you proceed, remember. Okay, so you can look for numericals from diffraction. Okay, so like I've told you, many a times you get questions to calculate the angular width, or sometimes half angular width also. Half angular width is more easy because in that case you only have to calculate theta. So I'm not going to discuss any numericals, for diffraction because those are very easy numericals, and you have to use this equation itself. But be careful while calculating angular width of center maximum, or sometimes half the angular width also. So this is about, diffraction of light. Thank you.